Welcome back. It's time for another deep dive into number theory.
Always fun to dive back into this.
Definitely. Last time we were looking at those amazing prime numbers.
Right.
This time we're going to tackle something that might seem a little bit basic at first.
Okay.
Euclidean division.
Uh-huh.
I think most people might remember that from like grade school as division with a remainder.
Right.
But we're going to go way beyond that.
Yeah, there's a lot more to it.
Yeah. It's got some pretty deep implications, actually, even for STEM folks out there.
Absolutely.
So to help us unpack this, we're using a couple of sources.
Okay.
We've got an excerpt from the Wikipedia page on Euclidean division, and we've also got a BYJU learning resource. And this one is about Euclid's division lemma.
Oh, okay.
So to set the stage, we all know Euclidean division.
Yeah.
It's about dividing integers.
Yeah,
And we get a quotient and a remainder.
exactly.
So it's like, simple example, 9 divided by 4.
Okay.
We get a quotient of 2 and a remainder of 1.
Right, but the really interesting thing is that the quotient and the remainder, they're unique.
Oh, okay.
And that's not something that we always emphasize enough, I think, in basic math.
Uh-huh.
But that's what makes Euclidean division so powerful.
So it's not just the dividing and getting a quotient and a remainder.
Right.
It's the fact that those two things, the quotient and remainder, are unique.
Precisely.
That leads to, well, I'm guessing some pretty powerful stuff.
Exactly.
Like what kind of stuff?
Well, so it applied in so many fields: cryptography, computer science.
Okay.
And, you mentioned this earlier, but the Wikipedia article actually mentions
Yeah.
the Euclidean algorithm for finding the greatest common divisor.
Oh, the GCD.
The GCD, right?
Okay.
Biggest common factor
Yeah.
that divides two given numbers without leaving a remainder.
So that's used in a lot of different areas, right? I remember like simplifying fractions.
Simplifying fractions, absolutely.
Okay.
And then cryptography, as you mentioned.
That's right. Really important concept.
And they're specifically saying that the Euclidean algorithm is built on Euclidean division.
It is, yeah.
So how does that work? How is an algorithm for finding the biggest common factor related to this simple division with a remainder?
Well, the BYJU piece does a really great job of breaking it down.
Okay.
Essentially, it leverages Euclid's division lemma,
Okay.
which is, I guess, the formal way of stating this whole concept.
Okay.
And it uses it repeatedly. So it applies division to the divisor and the remainder from the previous step.
Oh, okay.
And the last non-zero remainder that you get, that's your GCD.
Oh, okay.
So they have a good example in there of finding the GCD of 980 and 78.
Oh, perfect. Should we walk through that?
Yeah, let's do it.
Okay.
So you start by dividing 980 by 78.
Okay.
That gives you a quotient of 12 and a remainder of 44.
Mm-hmm.
Now, instead of focusing on the 980 and 78, we shift our attention to 78 and 44.
We divide 78 by 44.
Okay.
You get a quotient of 1 and a remainder of 34.
So we just keep doing this over and over again.
Exactly, yeah.
With the new numbers.
Yep.
Okay.
So next you divide 44 by 34.
Okay.
Quotient of 1, remainder of 10. Then 34 by 10, quotient of 3, remainder of 4.
Okay.
Continue, divide 10 by 4. Gives you quotient of 2, remainder of 2.
Okay.
Finally, you divide 4 by 2, and that gives you a quotient of 2 and a remainder of 0.
0. So we're done.
Yeah.
And the GCD is 2, the last divisor.
Exactly.
It's pretty neat.
It's an elegant process, isn't it?
Yeah, it is. It's kind of cool to see how it all unfolds step by step.
Yeah.
The Wikipedia article also mentions modular arithmetic.
Oh, yeah.
Can you remind me what that is again?
Sure. So think of a clock face.
Yeah, okay.
It's a cycle of 12 hours. When we go
Right.
past 12, we start over from 1.
Right.
That's modular arithmetic in action.
Okay.
Essentially, it deals with remainders after division. The remainder becomes our answer in the modular world.
Okay.
And Euclidean division, with its emphasis on the unique remainder, it forms the basis of this whole branch of math.
So if we say 15 is congruent to 3 modulo 12,
Right.
we're saying they both have the same remainder when you divide by 12.
Exactly.
So?
And that's used in cryptography, computer science, all sorts of things.
So this is definitely more complicated than just simple division.
Yeah.
I mean, it's all based on it, but it gets
does.
pretty complex pretty fast.
It really does.
The Wikipedia article also lays out the theorem itself formally.
Right.
It says, for any two integers, A, which is the dividend,
Yes.
and B, which is the divisor, and B can't be 0,
Right.
there exist unique integers, Q for quotient and R for remainder,
Mm-hmm.
such that A equals B times Q plus R.
Exactly.
Okay. And so they also make a point of saying that the remainder,
Yeah.
it's always non-negative.
Right.
And it's strictly less than the absolute value of B.
Yes. Very important.
So like in our 9 divided by 4 example,
Yeah.
it would be 9 equals 4 times 2 plus 1.
Exactly.
So we've got our dividend is 9, our divisor is 4, quotient is 2,
Mm-hmm.
and our remainder is 1, which is less than 4.
Yeah. Perfect example.
Okay, so we've got the basic concept.
Right.
We kind of get how it's important,
Yeah.
but why should someone who's not like, a mathematician
Right.
care about this? Like, what's the real world?
That's a great question.
Relevance.
Yeah. So that leads us into some of the practical applications of this, seemingly abstract concept.
So, like, we talked about cryptography briefly.
Right.
How does Euclidean division play a role in, like, keeping my information secure online?
Okay, well, imagine you're sending a secret message online, and you
Okay.
want to make sure only the intended recipient can read it.
Right.
So that's where cryptography comes in.
Yeah.
It uses complex algorithms to encrypt your message, basically scramble it up, make it unreadable.
Uh-huh.
And many of these algorithms, specifically those based on what's called public key cryptography,
Right.
they rely heavily on the principles of modular arithmetic,
Okay.
which, as we discussed, comes directly from Euclidean division.
So Euclidean division is helping to keep my data safe.
It is, yeah.
That's pretty cool.
Yeah, it's amazing.
And you also mentioned, like, signal processing. The Euclidean algorithm is used there, too.
Yes.
Can you kind of, like, walk me through that?
Sure. So imagine you have an audio signal
Okay.
and it's contaminated with noise.
Okay.
You want to clean it up.
Right.
You might want to analyze the frequencies that are present
Okay.
in both the signal and the noise.
Got it.
And the Euclidean algorithm can help to identify the greatest common divisor of the frequencies,
Okay.
which can then be used to filter out the unwanted noise.
Oh, okay. So it's like, it's helping to, like, isolate what you want and get rid of what you don't want. That's really interesting.
Yeah, it's a clever application.
It is. It is.
And you mentioned before
Yeah.
that the Euclidean algorithm is actually quite straightforward
Yeah.
to implement in
Whoa.
computer programs.
Right.
It's actually one of the earliest known algorithms.
Oh, wow.
And it's a staple in computer science courses.
So it's really like a bridge between,
Yeah.
like, the theoretical math
Yeah,
and the actual, like, concrete, programming.
exactly.
That's pretty cool.
Yeah, it's a great example of how math can be used to manipulate the world around us, even the digital world.
I like that.
Yeah.
So we've got cryptography, signal processing.
All right.
I'm sure there's tons more applications out there.
Oh, absolutely.
But, one thing that was interesting in the Wikipedia article was that they mentioned that the uniqueness of the quotient and the remainder.
Yeah, it's
Yeah.
not always guaranteed.
What?
Yeah. So when you're dealing with other mathematical structures like polynomials, it's not always the case.
So remind me what a polynomial is.
Right. So in simple terms, polynomials are expressions
Right.
that involve variables
Huh?
raised to powers
Mhm.
and combined using addition, subtraction, and multiplication.
Okay.
So something like x squared plus 2x minus 3, that's a polynomial.
Okay. And so how does Euclidean division work with those?
It's similar to the division of integers,
Okay.
but instead of focusing on the size of the numbers, we consider the degree of the polynomials.
The degree.
The degree, yeah, which is essentially the highest power
Right.
of the variable in the polynomial.
Got it.
So in that example, x squared plus 2x minus 3 has a degree of 2.
Okay.
And the remainder, like with integers, has to have a lower degree than the divisor.
Okay.
But unlike with integers, this condition doesn't always guarantee a unique quotient and remainder.
Interesting.
Yeah.
So the rules change a little bit.
They do, a little bit.
Okay, that's interesting.
Yeah.
So we've got Euclidean division. We kind of get how it works.
Mm-hmm.
We're starting to see all these cool connections to all these different areas.
Absolutely.
This has been a really, really cool conversation so far.
It has.
I'm really interested to see where else we can go with this.
Me too. Yeah, there's so much more to explore.
Definitely.
Yeah, probably.
But I think for now, let's take a little break.
Okay.
And then we'll come back and we'll dive into some more specific examples
Sounds good.
of how this is used.
I'm excited.
Yeah, me too.
Welcome back. We were talking about some of the practical uses of Euclidean division.
Yeah. Like before the break, we were talking about how the Euclidean algorithm is used to find the GCD,
Right.
which we said is useful for, like, simplifying fractions.
Yeah.
But you mentioned it's used for more than that.
It is, yeah.
Can you give me a real-world example?
Absolutely. So let's look at cryptography.
Yeah.
It's a field where Euclidean division plays a really crucial role.
Okay.
One common encryption method is RSA, and that relies on the difficulty of factoring large numbers into their prime components.
Got it.
And so finding the GCD, how does that tie into that?
Yeah, how is finding the GCD related to, like, the security of encryption?
Well, the Euclidean algorithm can be used
Okay.
to efficiently determine if two numbers share a common factor other than one. If they do, it means at least one of the numbers isn't prime.
Right.
And so this ability to quickly test for primality, it's essential in generating the large prime numbers that are needed for RSA encryption keys.
So finding the biggest common factor, which is something we can do because of Euclidean division,
Right.
is actually helping keep our online data safe.
It is, yeah.
That's amazing.
Pretty cool, huh?
Yeah.
And the applications extend beyond just cryptography, for example, in signal processing.
Oh, right. You mentioned that before.
Yeah.
Can you help me visualize how that works? Like, how is an algorithm for finding the GCD applied to, like, audio?
Okay, so imagine you have an audio signal that's contaminated with noise.
Got it.
And you want to clean it up.
Yeah.
So you might want to analyze the frequencies present in both the signal and the noise.
Got it.
And the Euclidean algorithm can help identify the greatest common divisor of the frequencies, which can then be used to filter out the unwanted noise.
Okay, so it's helping you, like, isolate
Yeah.
what you want from what you don't want.
Exactly, yeah.
That's pretty cool.
It's a clever application.
It is. It is.
And, you mentioned this before, but the Euclidean algorithm is actually really straightforward
Yeah.
to implement in computer programs.
Yeah, you said it's one of the earliest known algorithms.
It is, yeah, one of the earliest known.
Oh.
And it's a staple in computer science courses.
So it really is like a bridge between these abstract mathematical ideas and, like, the concrete world of programming.
Exactly.
That's really neat.
It is.
So we've talked about cryptography, signal processing.
Right.
I'm sure there's tons more applications out there. There's so many.
But one thing I wanted to go back to,
Right.
We talked about how important the uniqueness of the quotient and the remainder is.
Right.
What if that wasn't true?
That's a great question.
Like, what would happen?
Well, it would introduce a level of ambiguity and unpredictability into many mathematical concepts.
Okay.
So, for example, if the Euclidean algorithm didn't produce a unique GCD, it would be much harder to develop those reliable encryption schemes.
Right.
And think about error-correcting codes.
Yeah.
If those remainders that we talked about before, they weren't unique, it would mean the receiver wouldn't be able to decode the message and correct errors.
Oh, okay.
So it's really important.
So the uniqueness property is crucial.
It is.
For making sure that all these systems we rely on work the way they're supposed to.
Yeah.
That's really interesting.
It is.
This has been a really, really cool discussion so far.
Yeah, I'm enjoying it. I'm really interested to see what else we can learn about Euclidean division.
Me too. There's a lot more to talk about.
So welcome back. We've been deep diving into Euclidean division.
It's been a fun one.
It has. It really has. We've talked about what it is, why it's important, how it's used in all sorts of cool stuff.
Yeah, all over the place.
But there's one more thing I want to touch on before we wrap up.
Okay.
We mentioned earlier how Euclidean division is actually, like, crucial in proving the fundamental theorem of arithmetic.
Oh, yeah, the big one.
Yeah, which says every integer greater than 1 can be uniquely expressed as a product of prime numbers.
That's right, a cornerstone of number theory.
Yeah, it's basically saying, like, prime numbers are the building blocks of all integers.
Absolutely.
So how is Euclidean division involved in proving that?
So the full proof, a little too involved probably.
Yeah, that's fair.
For our chat today. But I can give you a little, like, sneak peek.
Yeah.
Of how Euclidean division comes in.
Okay.
The proof often relies on what's called proof by contradiction.
Okay.
So it starts by assuming that there exists an integer greater than 1 that cannot be expressed as a product of primes.
So we're assuming the opposite of what the theorem says.
Exactly, yeah. We're saying, okay, what if this isn't true?
Got it.
And then using the properties of Euclidean division, specifically that whole unique quotient and remainder thing.
Right.
We show that this assumption actually leads to a contradiction.
Oh, okay.
And that contradiction basically means our initial assumption must be false.
Okay.
So therefore, every integer greater than 1 must be expressible as a product of primes.
So we're using Euclidean division to back up
Yeah, exactly.
this really important concept about prime numbers.
Exactly.
That's really interesting.
It is. It really highlights that, math, everything's connected.
Yeah.
In kind of cool ways.
Everything's related.
Yeah.
I'm curious though. Are there any new areas of research or new technologies where Euclidean division is popping up?
That's a great question. Research is always kind of pushing the boundaries.
Yeah.
I can't speak to every specific case.
Of course.
But there are definitely areas where the principles of Euclidean division are probably involved.
Okay.
For instance, quantum computing.
Right.
That's a really hot field right now.
Yeah.
Exploring, using quantum mechanics for all this crazy complex computation.
Yeah.
There's a lot of work going on right now on developing algorithms for things like factoring large numbers.
Oh, which we were just talking about with cryptography.
Exactly.
So this is quantum cryptography.
It could be, yeah, absolutely.
Wow, so Euclidean division is even involved in that.
Yeah, it's very likely that these concepts will be important there.
That's really amazing.
It is, yeah.
It's pretty cool to see how something so seemingly simple can have such a big impact.
Yeah, absolutely.
Even on stuff that's on the cutting edge.
Yeah, it's really a testament to the power of those fundamental math ideas.
It is.
And their ability to just adapt and evolve with technology.
Yeah, I think it's safe to say we just scratched the surface of Euclidean division today.
We did.
Yeah. We went from its role in basic arithmetic all the way to these super advanced technologies.
Absolutely.
And it's clearly much more profound than it might seem at first.
It really is.
So thanks for joining us for this deep dive. I hope you've learned something new and that you've gained a new appreciation for Euclidean division.
Me too.
Until next time, keep those minds curious. And remember, even the most basic ideas can hold the keys to unlocking some pretty amazing insights.
Absolutely.